Welcome to day 21 of the macOS and iOS Security Internals Advent Calendar. Today we will be looking into the topic of zone element hardening. So what do I mean by this? Basically, when you look at the XNU kernel, we have a bunch of allocators there, but the most important allocator is actually the so-called zone allocator. It is implemented in the mach part of the kernel and basically powers the zalog and friends allocator functions. And it is the most important allocator because when you look at the other allocation functions, you will realize that they in the end, deep down, just wrap around the zone allocator in various ways. So the idea of this allocator is basically that memory is divided into so-called zones. Zones actually have a name, and they are basically of the same size. Within one zone, all memory blocks, all zone elements have the same length. So it's for grouping allocations together so that, for example, the same data type always ends up in the same kind of zone. We are not going into details here. This is just the only information you need here. So since iOS 10 or macOS Sierra, there's basically metadata available for every single zone element. That wasn't the case before, but ever since then, every zone element is somehow connected to a piece of metadata so that the allocator knows at any time certain attributes of zone elements, for example, the size. And this is nowadays used by Apple to add more and more mitigations into the kernel to fight memory corruptions inside the heap. So before iOS 14 or macOS Big Sur, the allocator was different. It actually changed a few times since then. But the allocator was different, and the thing was, when you freed a pointer, there was no check if the pointer you freed was actually aligned to the beginning of a zone element. So you could actually free pointers by override or something like this, pointer override. You could free pointers that were actually not pointing to the beginning of a zone element. So they were basically in the middle of a zone element. And so you would pollute the free list of a zone with pointers that are actually in the middle of two elements. And the graphic here symbolizes this. We have two zone elements that are adjacent to each other. And now we want to free the first one. But we're actually not freeing the pointer to block 1, but we're actually freeing a pointer block 1 plus X. So what happens is that now this unaligned memory block ends up in the free list of our zone. And that's bad because now on the next allocation, our next allocated block 3 will actually be now a pointer that is not aligned. So block 3 is now actually overlapping with block 1 and block 2. Block 1 is not the problem because that's theoretically now freed and the code doesn't accept it to contain data anymore. But block 2 is still fully in use, and so block 3 now partially overrides the content of block 2. So you basically have some kind of memory corruption going on here by having a partial pointer override, for example, in the beginning, and now you have actually a bigger override that way. So so Apple silently did protection against this. Not sure if they did this intentionally or if it was just a side effect of the new heap structure, because the new heap works a bit different. Because nowadays, when you have a free, namely a set_free _x, what happens is it will sooner or later call the function zone element resolve. And among other things, the zone element resolve will actually detect if an element is unaligned. What you see here is a part of the code, and down here you can see it is trying to determine the index of an element within the memory chunk. And here it basically validates if this memory chunk is actually aligned. And if it's not aligned, it will cause a kernel panic. So with this new allocator, it is no longer possible to free a memory pointer that is not aligned into a free list. Actually, there is no real free list anymore. But this is something that you would learn if you have more in-depth knowledge about the zone allocator. Yeah, but this is basically the point here. We can no longer do this, so this attack is basically dead. So another thing that happened in XNew is kernel data structures are usually allocated in a specific type of zone. Usually it's either because they have a fixed size or because there's an actual own zone for this specific data type. And an attacker often cannot put its attacker data into the same type of zone. They sometimes can do that, but not usually. And so the problem is they usually want to find a way to confuse the kernel into using their data instead of a data object. And so that usually happens via tricks like use after freeze with a garbage collection in between, or partial pointer overrides. But the trick is always the same. We're trying to make the pointer point to a different kind of zone where we can put our attacker controlled data. And so that is the attack. We basically confuse the kernel with data that belongs to one zone instead of the zone that it should actually be. So to fight this, Apple has already for a long time now created a new function that is called zone_require. So zone_require is basically doing exactly what it says. It requires something to be of a specific zone. So what it actually does is it takes the element, looks up the metadata for that element, and within this metadata it tells us what zone this element is allocated in. And then the function simply compares if the required zone is exactly the one that this element comes from. And if it's not the case, it will immediately kernel panic. So this basically allows now the code to always require that certain data elements are from the right zone they're supposed to be in. Otherwise, they will always kernel panic. To make this even easier, Apple has actually created a number of hard-coded positions for certain zones, like zones for tasks, zone for procs, and something like this. And so they now have zone require ID because they have a hard-coded number for each zone, what position they should be in the zone array. And so that's basically just a faster way to do the check instead of having a little bit slower check here. Okay, so that is the idea. Since they have this, it is now no longer possible to easily just like confuse the kernel with a different zone with the data, because the zone require will just immediately detect that this is, for example, not a task structure, it is not a proc structure, and so on, because it's coming from the wrong area on the heap. There was a while when Apple had implemented this code incorrectly, so it could be tricked, but nowadays it's hardened against this kind of trickery. So, and the last thing I want to talk about, which is not necessarily the last mitigation reusing metadata, but this is the last thing I talk about today, is the zone element overflow attacks. So within XGNU or most other kernels, it is a very common operation that you copy data between user land and kernel land, be it either parameters in or results out. And when you have very small amounts of data, usually the kernel code uses stack buffers. But when the data goes over a certain threshold, then it will start using kernel heap instead of kernel stack for copying in data or copying out data. And the thing is, because it's using the kernel heap, usually what we have to deal with are zone elements. And there have been historically a bunch of these overflows where we have either an overflow or an overread. And the problem is usually that there's a missing size check. So the length of the kernel buffer is not verified before we copy something in. And now again, if we have zone elements involved in this, we have metadata to fight this. And this is exactly what Apple did. They basically modified the copy validate function. This is a function that exists for a long time to validate the kernel target or kernel source in a copy in or copy out operations. So there were stuff in there like validating that it's actually a kernel pointer or validating that the size is not over a giant threshold, because then we have always the kernel panic. These kind of validations are done inside this copy validate function, but now they have also added checks for the size of zone elements. So there's the zone element size check nowadays in there that basically will validate if or how big this element is on the zone, and if it's too small for the amount of data that is requested for the copy operation, it will kernel panic again to basically stop a buffer overflow before happening, but also to stop a buffer overread before it's happening. Yes, and this is our short intro about zone element hardening. This is the end of the door for today. So I wish you a great day and see you tomorrow for the next door in the Advent calendar.